All right, in this second half of the section 10.3, we're going to look at, in particular, arc length and surface area with parametric equations. So these two ideas obviously involve integration, but parametric equations are really good dealing with arc length, surface area. They're really good at dealing with lengths. The area under the curve is not as crucial, at least not for this class, with parametric equations. So let's take a look at arc length using the parametric equations. So the parametric equations I'm going to use are x equals a function of t, which we'll call f of t, and y equals a function of t, which we call g of t. So in this, the arc length can always be calculated by integrating from a to b the derivative of f squared plus the derivative of g squared, all obviously with respect to t. Now be careful here. The a and the b, since we're dealing with derivatives with respect to, did I say derivatives? Since we're integrating with respect to t, those a's and b's have to be t values, okay? So they have to be values for t. So that's the idea. Now, by the way, this does mesh up really well with the arc length that we saw way back in chapter 7. It's actually the same thing, and I will show you how we get that. All right, so let's do an example first. I want you to try this on your own. It's not a real hard, arc length's not real hard to calculate. So I want you to find the arc length of a curve on this given interval. So the curve is given to you by the parametric equations x equals 3t minus t squared and y equals 2t to the 3/2 power. And we're going to find the arc length on the interval from 1 to 3, t in between 1 and 3. Go ahead and find that. All right, so hopefully you went ahead and did that. So I have it sort of set up here. We know the arc length is given to us by this formula, uh, square root f prime t squared plus g prime t squared from a to b. And so what we end up doing is we end up, looking at taking derivatives of my x function and my y function with respect to t. So with respect to t, the derivative of this x function is going to be 3 minus 2t. So I just replace this f prime with 3 minus 2t. And I replace that g prime with the derivative. By the way, the derivative of this 3/2 times 2 is 3. Then we get t to the 1/2 power. 3/2 minus 1 is 1/2. So we end up with that as my arc length. Now, obviously the A and the B, since our t values are between 1 and 3, lower value is 1, upper value is 3. So that's the setup. And then as far as actually calculating this goes, this is just a calculator function. So integrate from 1 to 3, this thing. I ended up with about an 8.86. I got 8.86114919 on my calculator. So it's roughly about 8.86. Again, that's rounded to 2 decimal places. All right, but that's the idea. So that's how you do arc length. And by the way, I did, I believe, graph this. So what the graph of this actually looks like, it looks like this weird curve that starts at 2, 2 and curves up and over. And so how long that actual curve is the arc length. Okay, so that's what we ended up with. Now, one thing I wanted to mention um, earlier that I talked about, I said this is actually lines up with what we saw in chapter 7. If you remember what we did in chapter 7, what we had is we had a situation where it was an arc length of 1 plus a derivative squared, although it was called f of t. I'm going to call that g of t. I'm going to use the y equals. And we did everything with respect to x. All right. Now, this actually is the exact same thing that we have here if x and t are the same variables. In other words, if we had a parametric situation where I let x be equal to t and then y is equal to some function of t, well, what would have happened? Well, this f prime of t, this one, would have just been 1, so we would end up with 1 squared, which is just 1, and then obviously dx and dt would be the same because x and t are exactly the same thing. So what we have with the parametric is actually a more generalized version of what we dealt with in chapter 7. Okay, what we dealt with in chapter 7 had this 1 plus. Well, now we see that that 1 plus is just the reason we have that is because the derivative of t, again, if x is equal to t, is 1. So there we go. That's the idea behind arc length. I'd like you to try one of these on your own. So push pause on the video and find this arc length. Okay, so this is the setup. X equals e to the t plus 2, y equals 2t plus 1. We're going to find that arc length between negative 2 and 2. So arc length, this formula, we take f prime of t, that's the derivative of the x function with respect to t. If you'd rather, again, you could, the f and the g are actually interchangeable. It doesn't matter which one you call the f, and which one you call the x, and which one you call the y function. But we'll use f for the x. So derivative of this is e to the t plus 0. So just take e to the t. Underneath the square root, e to the t squared plus, well, derivative of the y is a 2. So integrating the square root of e to the t squared plus 2 squared, and then my a, lower bound of t is negative 2. My b, which is the upper bound of t, is a positive 2. And that's something that you can plug into your calculator. Once you actually plug that into your calculator, excuse me, you end up with about 11.89. Okay, so you get an arc length of about 11.89 in this case. And again, that's the length of that curve that's sketched out here between values of t, which are negative 2 and 2. So arc length is a fairly straightforward thing to deal with. Obviously, we can do arc lengths now of things like ellipses and hyperbolas over certain intervals. Now, remember, surface area kind of came out of arc length. And so what we're going to look at is two different surface areas. Surface area that I get when I revolve a curve around the x-axis. Now, if we're revolving it around the x-axis, then what we do as our radius, we take our y value as our radius. And if we revolve around the y-axis, we're going to take our x value as the radius. So it's just 2 pi and then y value times arc length formula type thing. 2 pi and then x value arc length formula type thing. Hopefully that all makes sense. But just for measurement, let's take a look at this situation here. Let me do this in red. If you're going to revolve around, let's say, the y-axis. Well, what the radius is going to be, it's going to be a distance from the y-axis, which is just your x value, all right, which we give as f of t. If you're going to revolve this thing around the x-axis, well, around the x-axis, what's the radius? Whoops. Well, the radius is from here all the way down. It's not a really good radius, but here all the way down, and so it's a y value, okay? So that's the idea. Revolve it around the y-axis, and the radius is how far over you are in terms of x, okay? So that's the idea. The formulas are pretty, like I said, pretty straightforward. There we go. So here's what I'd like you to do. I'd like you to find the surface area generated by revolving this curve around the x-axis. Push pause on the video and go ahead and do that over the interval from 0 to 3. Okay, so hopefully you went ahead and did that. So we're going to be revolving this around the x-axis. So my surface area that I need to use has to have the y value function right here in front of the square root. Okay, so that's the idea. Now, the main thing people will get wrong on this, they'll do the a is 0, lower bound, b is the upper bound, that's 3. They'll get the derivatives right, 1/2 t as the derivative of x, 1 as the derivative of y. But what people will often get wrong is this front component. People will throw the derivative in there when they're actually supposed to throw in the actual function of y. So you need to plug in t plus 3 as your g of t, and when you do that, make sure it goes in parentheses when you type it in on your calculator. If you put t plus 3 and it doesn't have parentheses, then your calculator thinks that you're multiplying the 3 times this square root, but the t is sort of all by itself. So you want to make sure that that t plus 3 gets treated as the whole function g of t here. All right, so that's the idea. And in my case, this surface area came out to about 114.20 when I rounded this to 2 decimal places. So that's the surface area that I ended up with. All right, I want you to do another one. Let's take this same curve, this same interval, but instead of revolving around the x-axis, let's revolve around the y-axis. Push pause on the video and go ahead and try to do that. All right, so revolving this thing around the y-axis, the only thing we need to change is this function in front of our square root. So once again, we're going to go from 0 to 3, so 2 pi, 0 to 3. Function in front of the square root will change, but underneath the square root, we're going to have 1/2 t, because that's the derivative of x, and then 1, because that's the derivative of a y, both with respect to t. So this function obviously changes because we're spinning around the y-axis. The distance from the curve to the y-axis will be whatever the x value is. So we replace that f of t with a 1/4 t squared. And then from this point out, we just multiply and calculate, use our calculator to do that. We end up with I ended up, I should say, with a surface area of about 21.49 rounded to 2 decimal places. So that's the idea there. Now, obviously, I've been using the letter T for everything. You don't have to every time. If you're using trig functions, sometimes the parametric equations will be written with respect to thetas instead of with respect to t's. So none of the calculations actually change. None of the ways you plug it in your calculator changes. They just have different letters. So why don't you go ahead and try to find the surface area generated by revolving this curve around the x-axis, and push pause on the video and try that. Hopefully you did that. This one's a little bit complex, but that's okay. As far as taking derivatives, it's not that crazy. X equals theta plus sine theta, y equals theta plus cosine theta. Um, Now our surface area formula is written in t's. It doesn't matter if you use t's or thetas in this thing. I'm just going to use t's when I type it in because my calculator mode already gives me a t when I hit the variable button. But if you wanted to switch it over to thetas, or in fact, you could use whatever variables you like. So what I'm going to do, first off, realize that since we're dealing with around the x-axis, we have to have our y value as our g of t. So I put t plus cosine t instead of theta plus cosine theta times the square root. Now the derivative of x, the derivative is going to be 1 plus cosine of theta. I use t, so 1 plus cosine t, and all of that gets squared in a parentheses or in a brackets, plus the derivative of y is 1 minus sine theta. So 1 minus sine t squared is also underneath that square root. We're integrating from 0 to pi over 2. Make sure your calculator is in radians mode when you do this. And what I ended up with when I punched that all into my calculator is 23.24 roughly. Okay, it gave me 23.24332 blah blah blah, but that's what happened. So now we see how to get the surface area of anything that we are looking for. At least anything that we're looking for that can be written in terms of parametric equations. By the way, these were kind of really weird functions. Uh, let's go ahead and graph those out real quick. The little section here in red is my curve. So I'm going to rotate that around the x-axis. That is the curve from 0 to pi over 2. If you wanted to look at a bigger curve, you could have done that too, but that's the idea there. You get something like this. So by the way, that curve, if you go from like 0 to, let's say, 7 pi, looks a little different. Does a kind of a weird change over there. It gives you kind of jumping up and going on this angle here, interestingly enough. So that's what's happening. So we take this bit of the curve, rotate it around the x-axis. And that is it for section 10.3.